Hello, calculus students. This is Bert Dixon. Today's lesson is going to be on section 7.6, and we're going to talk about how to define inverse trigonometric functions and the derivatives and integrals associated with the inverse trig functions. So what we first need to talk about is the fact that a sine graph or a cosine graph, these are functions because they pass the vertical line test. In other words, if I draw a vertical line anywhere along the curve, it's only going to touch the graph in one point at a time. So that's called the vertical line test. And so we see that sine is a function because no matter where I draw a vertical line, it only touches the graph once. Okay. However, we're interested in looking at the inverses of sine and cosine. And notice that if I switch the x and the y values, a sine graph looks like this. And it's no longer a function because it fails the vertical line test. If I draw a vertical line now, it crosses in multiple places. Or if I draw it right here, it would touch on the tips. So we can see right away that this is not a function. And so in order to make inverse sine into a function, we have to restrict the domain of the original sine graph before we take its inverse. And so in order to make this pass the vertical line test, we're going to look at just one cycle of the sine function from here actually that's too far, from here to here. So from negative pi over 2 to pi over 2, because that's the largest span that we can get and still have it pass the vertical line test. So what that looks like on this graph is from here to here. Notice that if I go a little bit further in either direction, it's going to fail the vertical line test. So now our inverse sine graph is only here. Okay, and the reason why we need this to be a function is in order to do calculus with it, in order to take derivatives and antiderivatives, it needs to be a continuous differentiable function. And if it's not a function, none of the stuff we learn in calculus applies. And just as we've seen when you learned to do triangle trigonometry in geometry, when you type in something like the inverse tangent of 1.4, your calculator gives you only one answer. Same thing if you type in inverse sine of 0.6. Your calculator only gives you one answer, and that's because it's treating the inverse sine as a function. It's the inverse sine function. And so the only way your calculator can do that is if we agree on a restricted domain from our original sine graph. And that's true for all of these trig functions. I'm focusing on sine right now, but we could do the same thing for cosine and tangent and cosecant and so on. Okay, and we will talk about those in a couple minutes. Okay, so now that we understand the need for making this into a function, notice that there are different places mathematicians could have decided, oh, we're going to use this part of the graph, so we're going to go from pi over 2 to 3 pi over 2. Or they could have decided we're going to go from negative 3 pi over 2 to pi over 2. So it was really an arbitrary decision, but it makes sense to choose an interval that surrounds 0, and so that's why they chose from negative pi over 2 to positive pi over 2 for the restricted domain. As long as everyone agrees that that's what we're going to do, then like I said, it's arbitrary. We just needed to pick a piece of the graph that satisfies the vertical line test. And so this is what was chosen for sine. We can do something similar for cosine. Cosine, for the same reason, since I can draw a horizontal line on a cosine graph, that means that would fail the vertical line. Since a horizontal line on the cosine graph touches the graph in multiple places, then a vertical line on the inverse cosine graph would touch in multiple places as well. So restricting this one the same way wouldn't work. If I tried to go from, like we did with sine, if I went from negative pi over 2 to pi over 2, that would still fail the horizontal line test on the original graph, meaning it would fail the vertical line test on the inverse graph. And so to restrict the domain for cosine, mathematicians chose to start at 0 and go to pi. So 0 to pi. And so what that gives us is this part of the graph is our inverse cosine graph. So this is what we agree upon for our the restricted domain on the original cosine graph gives us this curve for the inverse cosine graph. So that is the piece of the graph that we're keeping to make it into a function. And then we can do something similar with sine. With tangent. Tangent repeats over and over again, so it's natural to just take one cycle of the tangent graph, and then that makes this into this for our inverse tangent graph. And so that's restricting it also from negative pi over 2 to pi over 2, but notice that it's an open interval for this one because we can't actually plug in negative pi over 2 or pi over 2 to the tangent function. Those are asymptotes. So with these two graphs, the secant and the cosecant, again, we can just take one cycle. So if we take this and this, so from negative pi to positive pi, that will pass the horizontal line test, which means the inverse would pass the vertical line test. And so we see those restricted domains here. Let's see, my page got a little bit compressed, so let's see if I can move this out of the way. Okay, so we see these are the accepted restricted domains from the original function. So we restrict this sine graph from negative pi over 2 to pi over 2 to make the inverse into a function. For cosine, 0 to pi. For tangent, I talked about that one, negative pi over 2 to pi over 2. And same thing is similar for cotangent, but it's from 0 to pi. And then secant, arc secant, we have to make sure we don't include the asymptotes, and so that's why this is broken into two parts. So it's basically from 0 to pi, but we have to eliminate pi over 2 because that's not part of the domain originally. And then same thing for cosecant. It goes from negative pi over 2 to pi over 2, but cosecant is undefined at 0, so we have to take care of that discontinuity there. And so those are the restricted parts of the original 6 trig functions that we focus on to get the inverses. So this notation, arc cosecant, arc sine, that's just another way of saying inverse. So arc sine is the same as inverse sine, it's just a different way to write it. So you'll see it written in both ways in various calculus textbooks or even pre-calculus books. So I will usually write it using this notation, but understand that arc means the same thing as inverse. Okay, so now we can evaluate some inverse trig functions. So this is, again, the same thing as saying inverse sine of root 3 over 2. So normally, like when you learned triangle trigonometry in high school geometry, you said things like the sine of theta is 2 over 7, okay? Theta was an angle, so we take sine and cosine and tangent and so on, all 6 of the trig functions, but we put in the input for trig functions is an angle, and that is equal to some ratio. So when we do inverse sine, it's the other way around. We're putting in the ratio, and we're trying to figure out what is the angle. Okay, so what angle has a sine equal to root 3 over 2? And so if you think about on the unit circle, you have 0, you have pi over 2, you have pi. You might remember these special angles at 30 degrees, which is pi over 6, and at 60 degrees, which is pi over 3. The coordinates of these points, this point has coordinates 1, 0. This point up here has coordinates 0, 1. And then this is negative 1, 0, and so on. So what happens at these special angles, because of the 30, 60, 90 triangles that we get, in a 30, 60, 90 triangle, if the hypotenuse is 1, the short leg is half of that, and the long leg is root 3 times the short leg. So that becomes root 3 over 2. And so the coordinates for this point, horizontally, we're moving root 3 over 2. Vertically, we're moving 1/2. And then at the 60-degree angle, or pi over 6, they switch places. This becomes, let me change colors so I can make this clear. This segment is 1/2, and this segment is now root 3 over 2, giving us the coordinates 1/2 horizontally, root 3 over 2 vertically. And so we see for sine, we always focus on the y value. The sine of the angle is the y value of the point on the unit circle. And so we see that sine of pi over 3 is equal to root 3 over 2, and that's what we're looking at. And since we use a restricted domain for inverse sine, remember we're only going from here to here. When we're doing inverse sine, we're only focusing on this part of the unit circle. And so there are other places on the unit circle, for example, here at 2 pi over 3, this is negative 1/2 root 3 over 2. So there's another angle that has a sine value of root 3 over 2, but that's not our answer because we're only taking values because of the restricted domain for arcsine. We're only taking values in between negative pi over 2 and positive pi over 2, and the only angle there that satisfies that is pi over 3. So the answer to our first problem is pi over 3. Okay. To solve this one, we're looking for an angle. So we're looking for some angle equals root 3. So we're trying to figure out what is that angle that gives us a ratio of root 3. And so since we have roots in these 2 points, we have this point and this point, it's going to most likely be one of those. So let's try the two. If we look at the tangent of pi over 6, that would be the y coordinate divided by the x coordinate, because tangent is defined as y over x, or opposite over adjacent. And so in this case, we get 1 over root 3, which is also root 3 over 3. So that's not the one we're looking for. So let's try the other one. Tangent of pi over 6 is, of pi over 3 is root 3 over 2 divided by 1/2, and that is equal to root 3. So that's the one we're looking for. So that means the inverse tangent of root 3 is pi over 3. That's the only angle in this restricted domain, the yellow part that I have highlighted, that has a tangent ratio equal to pi over 3, equal to root 3, is at an angle of pi over 3. Okay, go ahead and pause your video and try C, and then press play when you're all done. To do part C, I'm going to draw another picture here, and this time we're going to look at the 45-degree multiples. So if I go to 45 degrees, which is pi over 4, then both the x-coordinate and the y-coordinate are the same. So if our hypotenuse is 1, this becomes 1 over root 2, 1 over root 2, or you might have learned those in high school as root 2 over 2 and root 2 over 2. Those are both the same, so it doesn't matter if you write it this way or if you read it this way, those are both the same numbers. So those are the coordinates that we get for a 45-degree angle. And so we're most likely going to be using one of those. Now, remember, for secant and cosine are related because secant is 1 over cosine. So they have the same domain restriction. So for cosine and secant, we only look at this part of the unit circle. We're looking, even though there are many parts, there are many places on the unit circle that have this ratio 1 over root 2, or just root 2. We're only looking for the one single value that happens in that highlighted region. Okay, so for sine, we highlighted that part of the unit circle. For cosine and secant, we look at that part of the unit circle. And so now we're looking for a ratio of root 2. So notice that if I do, so this means we're looking for the secant of some angle that would be equal to root 2. And so if I try pi over 4, let's see what the secant of pi over 4 is. Secant of pi over 4 is 1 over the cosine of pi over 4, which is 1 over root 2. And that is root 2. So we found our answer. So the answer to this, the angle that we're looking for, remember when we do an inverse trig function, we're looking for an angle. The angle that works is pi over 4. And so to do these problems, they require some knowledge of the unit circle. So if you don't remember your common values, like what are the coordinates for pi over 4 and 3 pi over 4, and so on, or along here I did pi over 6 and pi over 3. If you don't remember those common values, you may want to review those topics, or I can help you with that. If you visit me during office hours, I can give you a review of how the unit circle works and what the common values are that you would need to know. We don't want to have to rely on a calculator, and your calculator is going to give you decimal answers anyway. And so it's good to have knowledge of what those coordinates are at various points on the unit circle. Okay, so now we're getting into the calculus part of inverse trig functions. And so this is a table that shows you what all those derivatives are. What is the derivative of inverse sine, inverse secant, inverse tangent, and so on. So the answers are all given here. These can all be proved by doing implicit differentiation. For example, to prove the first one, all you have to do is, so if we want the derivative, if we want to know the derivative of inverse sine, let's call it y, then, sorry, if I say y equals inverse sine, and I take the derivative of both sides, then that would give me the derivative that I'm looking for. So that would be dy dx equals derivative of inverse sine. So that's what we're trying to find. But to find it, we're going to use what we know about the concept of what an inverse is. Inverses are opposites of each other, and so if I take the sine function of both sides, sine of y equals inverse sine, equals sine of inverse sine of x. So what I did from this equation, I just took the sine of both sides, and they should be equal. So here I get sine y equals the sine of the inverse sine. Those functions undo one another, and so we just get x. And so the sine of y equals x, and now I can take the derivative of both sides with respect to x. And so on this side, I get the derivative of sine as cosine of y times dy dx equals 1. And so then dy dx equals 1 over cosine y. And so now, to finish this off, we are going to need to draw a right triangle that fits the description of this original statement. The sine of the angle is equal to x. Now, sine is a ratio. If you remember from high school geometry, sine is a ratio of opposite leg over hypotenuse in a right triangle. So if we say this is angle y, the sine of angle y should be the ratio of opposite. So if we call this x over hypotenuse 1, then this triangle is consistent with this equation. The sine of y is equal to opposite over hypotenuse. So the sine of y is equal to x, which is x over 1. And so now if we use the Pythagorean theorem, this side is the square root of 1 minus x squared. Now that we have all three sides here, we can say the cosine of y. The reason why I'm doing cosine is because we want to know what that is. We're trying to get an answer in terms of x. And so the cosine of y is equal to adjacent leg over hypotenuse. So that's going to be square root of 1 minus x squared over 1, which is just square root of 1 minus x squared. So the cosine of y can be replaced by the square root of 1 minus x squared. So this means dy dx, 1 over cosine y is equal to 1 over the square root of 1 minus x squared, because that's what cosine y is according to this statement. Okay, so now we have the derivative is equal to 1 over 1 minus x squared, and that's exactly what it shows here. And so for all of these, if you wanted to prove any of these 6, you would start with an equation like this, name the inverse trig function y, apply the function to both sides like this. I took the sine of both sides to get rid of the inverse function, and then I took the derivative implicitly, and then I used a triangle, a right triangle, to find the third side, and then I'm able to come up with the trig ratio that I want. So I encourage you to try any of those and see if you can prove any of those 6 derivatives that are given in the table. Okay, so now we can use any of the derivatives from this table to calculate some derivatives, and we might have to apply the chain rule when necessary if we ever have anything besides an x inside any of these 6 trig functions. Then we would just replace all the x's with that expression and then apply the chain rule. So for example, number 2a here, if I take the derivative of both sides, dy dx, using the table and using what we just proved, is that the derivative of inverse sine is 1 over the square root of 1 minus x squared. And so this is in place of where the x normally is. So this would be 1 over square root of 1 minus this expression squared, and then times the derivative of the inside, and the derivative of the inside is 2x. So we end up with the derivative being 2x over the square root of, in this case it would be negative x to the 4th plus 6x squared minus 8, I believe is what you get if you simplify that. Not necessary that you expand that out, but this is what I would get for a simplified answer. Okay, so go ahead and pause your video and try example B, referring to the inverse cotangent derivative that's in the table above. Okay, so in this table we have 6x in place of where the x normally is, and so we're going to also have to put 6x in place of that x when we take the derivative. So the derivative dy dx in this case is equal to negative 1 over 1 plus, normally it's x squared, but in this case it's going to be 6x squared, which means we have to apply the chain rule and take the derivative of the inside also, which is 6. And so our final answer then is negative 6 over 1 plus 36x squared. Okay, and then in example 3, we're going to see that we could actually do these derivatives that we did in the previous 2 examples without using the table, let's say you forgot how to do one of the derivatives that's in that table. You tried to memorize them and you forgot one of them. And so you just go back and do it from scratch using implicit differentiation rather than using the derivative table above. And so we're going to do this same problem, but this time using implicit differentiation rather than using the derivative table. And so here's how this would look. We start with y equals inverse sine of x squared minus 3, and then we take the sine of both sides. So this equation is equivalent to saying the sine of y is equal to x squared minus 3. And from that, we can draw a picture of a right triangle. Remember that what's inside the standard trig function is an angle. So we can name that angle y, and sine is opposite over hypotenuse. So that means the opposite leg would have to be x squared minus 3 with a hypotenuse of 1. And so then using the Pythagorean theorem, this would be the square root of 1 minus x squared minus 3 squared. And so now when I take the derivative of this, I have cosine y dy dx equals 2x. And so dy dx, which is what we're trying to find, is equal to 2x over cosine y. It looks like we're done, but we don't really want a derivative that has x's and y's in it. We're trying to find the derivative as a function of x. And so here's where the triangle comes in. I can look at this triangle and see that the cosine of y is adjacent leg over hypotenuse. So that's just going to be the square root of 1 minus x squared minus 3 squared. And now we have dy dx written as a function of x. And notice that that is exactly the same as what we got up here. Except without using the derivative table, we just used implicit differentiation and drew the right triangle that's associated with that equation that we got. Okay, so go ahead and see if you can do the same thing for B. Redo problem B, but this time using implicit rather than using the derivative table. Okay, so this would be y equals inverse cotangent of 6x, which means if I take the cotangent of both sides, I get cotangent y is equal to 6x. And so drawing a right triangle from that description, y is our angle, cotangent is adjacent over opposite. So this would be adjacent 6x over opposite 1. And then by the Pythagorean theorem, this would be the square root of 1 plus 6x squared. And so now if I take the derivative, we have the derivative of cotangent is negative cosecant squared y dy dx equals 6. And so then dy dx equals negative 6 over cosecant squared y. And so from this triangle, we can see that cosecant y would be hypotenuse over opposite. And so cosecant squared y would be just 1 plus 36x squared. And we fill that in down here, and we get dy dx is equal to negative 6 over 1 plus 36x squared. That is exactly the same answer we got when we used the table. All right, so next we have integrals. So if we know these 6 derivatives from this table, then whenever we see expressions like these inside an integral, we'll know how to find the antiderivative. Because if I see, for example, if I see this inside an integral, I know the antiderivative is inverse cosine. If I see this inside an integral, I know that the antiderivative is inverse tangent. Okay, and so looking at example 4, this looks like square root of 1 minus something squared. So if I did a u substitution and said u equals 5x, then this part becomes u squared. And so u equals 5x, du equals 5 dx. So dx is going to get replaced by 1/5 du. And so now I have the integral of 1 over the square root of 1 minus u squared, and dx gets replaced by 1/5 du. And this looks just like, if we look at our table, looks just like inverse sine. And so this is going to be 1/5 inverse sine u plus c. And then we'll substitute the 5x back in again. So we get 1/5 inverse sine of 5x plus c. All right, so go ahead and pause your video and try example B. All right, so for example B, we would need to do a substitution. We want this to be u squared, so we have 1 plus u squared in the bottom, and that way it'll look like a tangent. So if we say u is equal to cosine of x, then du is equal to negative sine x dx, and we have a sine x dx here. We just need to get rid of the negative, so we could say negative du will replace sine x dx. And so this part that I circled gets replaced by negative du, and then the rest of it becomes 1 over 1 plus u squared. And so you'll recognize there's two different ways to integrate this. If we keep the negative inside, then we see that that is from our table. We see that that is inverse cotangent. If we leave the negative sign on the outside, then we could use inverse tangent. So what I'm saying is there are two different possible answers for this one. So this, as I have it written, we could say is inverse cotangent of u plus c, which would be inverse cotangent of cosine x plus c. So that's one way to do it. Or if I leave the negative on the outside, then I could say this is negative inverse tangent of u plus c, which would be negative inverse tangent of cosine plus c. So either way, we get some antiderivatives, for example, b. Okay, and then the last one, example C. This one is a little bit tougher because of the 9 in front. Remember to make it look like one of those 6 trig antiderivatives, we want it to look like this, 1 minus u squared. And so to get a 1 here, we have to get rid of that 9. And so what we're going to do is we're going to factor that 9 out first. So a little bit of algebra. If I factor out a 9 here, then that would be 1. And then think about what would be left here. I need something here so that when I multiply, when I distribute, I get the same thing that I started with. So the 9 happens here. What would have to go here is my question. So think about that for a moment. That would have to be 4/9, so that when I multiply by 9, I just get the 4x squared that I have up here. Okay, so we've factored out the 9, and now we can take the square root of the 9, and it becomes a 1/3. So I'm going to bring that out in front. Square root of 9 is 3, but since it's in the denominator, it's 1/3. So now we have this 1 minus 4/9 x squared dx. And remember, we want it to look like this. And so that means u would have to be 2/3 x. So u equals 2/3 x, du equals 2/3 dx. So dx is going to be replaced by 3/2 du. Okay, so then this integral becomes 3/2 du is replaced by dx, and then we have 1 over square root of 1 minus u squared, which is just inverse sine. These 3's cancel, so we get 1/2 inverse sine u plus c, and that is 1/2 inverse sine of 2/3 x plus c. Okay, so the methods that we used for those 3 examples, A, B, and C, for example 4, those methods can all be summarized in this integration formula table. Notice that we only really need 3 trig functions, because as I showed in example B, what we can do with inverse cotangent, we could do just as easily with inverse tangent. And so that's why for integration, we really only need to use these 3. There's nothing wrong with using the other 3, like I did in example B, but it's easier just to focus on these 3 antiderivatives. And so this formula here, we see the result of that in this problem. See how we originally had 9 minus 4x squared, and so our a was 3 and our b was 2, and so that ended up with u over a, which is our u in this case would be 2x, and so we ended up with 2x over a, where again a is 3. So you can use these formulas, or you can just do the substitutions like we did in examples A, B, and C above. If you understand how to do those substitutions, you don't really need these formulas. These are just, they're here in case you get stuck on a problem and you want to see how you would approach it. You can always try using these, but as I showed in those 3 examples, you don't have to have these formulas. You can come up with them just by your own substitutions. Okay, so in example 5, I'll show how you can use these 3 formulas. You do have to be careful when you use these formulas, because you still have to do the substitution necessary to get the du and the integral. I'll show what I mean by that, but you have to still do the substitution step. So these formulas just help you identify what a and u are, and so this denominator looks a lot like this, and so we see that if we make a equal to 6, a squared would be 36, which is what we want, and then that means u has to be 2x in order to make that u squared. And so here's where the substitution step comes in. So I have u equals 2x, du equals 2 dx, which means dx is going to get replaced by 1/2 du. If you don't do this step and you just plug directly into this formula to get your answer is going to be off by a factor of 1, because it won't have the 1/2 in front. And so that's where it's still important that you rewrite the integral. And so this is going to be 6 squared plus u squared, and dx gets replaced by 1/2 du. And again, if you didn't do that substitution step, then you wouldn't have the 1/2 in front. And if you just used the right side of the equation only and didn't do the substitution step, you'd be off by that factor of 1/2. And so now, according to the formula, we have 1/2, and our antiderivative is 1 over a, which is 1 over 6, inverse tangent of u, which in this case is 2x, over a, which is 6, plus c. And so we get, for our final answer, 1/12 inverse tangent of x over 3 plus c. Okay, so go ahead and pause your video and try B, and press play when you're all done. See if you can use the table up here to solve this one. All right, so this denominator looks a lot like this. We would say that a is 1, and we would say in order to make this part u squared, to match that, we would have to say u is equal to 2w. And so if u is 2w, then du equals 2 dw. And so dw gets replaced by 1/2 du. And so this integral then becomes 1 over, we have the square root of u squared minus a squared. So this would be it would just be u squared minus a squared. And then we have this w in front. And so we don't have w written down anywhere, but from this equation, we could easily get w equals 1/2 du, or just 1/2 u. And so this is going to be 1/2 u. And then in place of dw, we said here dw gets replaced by 1/2 du. So the 1/2 is there. And since this 1/2 is in the denominator and this 1/2 is in the numerator, those would cancel. So we just get 1 over u square root of u squared minus 1 du, which matches this exactly. So we get 1 over a, which is just 1. I'll go ahead and write it. 1 over 1 inverse secant of u over a, and that would be inverse secant of 2w plus c. And that's it for today's lesson. These are some good problems that you could try on page 424 to practice these concepts. And if you do odd problems, you can check your answers in the e-text. And if you do even problems, you can email me to get answers to those even numbered problems. Have a great day, everybody.